This segment is about finding D1. And let me start by saying it'll be easier to follow if you've already seen the segment finding Dn. Anyway, so from the basic diagram, we can see that D1 equals dl, the distance light traveled, minus the change in the distance light traveled over the time it was traveling from D1. So that's the basic equation we're going to use to find D1, because we already know dl from the observed data. So then all we have to do is find a way of calculating the change in the distance that light traveled. Now this formula can be rearranged like this to say dl, the distance light traveled, equals d1 plus the change in the distance that light traveled during the time it was traveling. And we just note that because that'll be useful later. Now, to find this change in the distance, we do it this way. Here's the original distance d1, which we divide up into a number of segments. Each segment has the length d. So we'll just note in passing that the number of segments is going to be the total length d1 divided by the length of each segment d. Now, as light was traveling, for the first segment that it traveled, that segment didn't expand very much. So that segment ended up with a distance of d plus 0 as the distance that light traveled passing through it. The last segment, d, expanded a lot because it took light a long time to get there, so it had more time to expand because of the expansion of space. So its distance that light traveled through is the original distance d plus some distance x, which is the amount it expanded by. Now, one of the things that makes this formula so difficult is that each of these segments will have expanded by a different amount as light was coming towards Earth. So the x's for each of these segments are different. Now, the compounding formula and the most precise formula for the total change in the distance for light while it was in transit is simply the sum of all these x's. And that is the compounding formula. Then from that formula, it's possible to calculate d1. Now, unfortunately, I'm not able to take that formula any farther, but I'm sure somebody watching this will be able to do that quite easily. Now, it is possible to come up with a simpler formula that we can use for approximate calculations without compounding, and we do it in the following manner. First, we make a quick approximation. We note that if we add up the lengths of the changes of the first segment, x6, because I was counting backwards, and the last segment, x1, then the difference in the changes for the light equals the change for x1, because this one was so small. Then, if we assume that we can get the same result by adding the second to last change in distance with the second segment from the beginning, in this segment space will have expanded a little bit more, and in this segment space will have expanded a little bit less. So let's assume that if we add x5 plus x2, we also come up with x1. And then we do it for each pair of segments all the way along. x4 plus x3, moving towards the middle, etc. And each of those pairs gives us the same total, x1. That's a quick approximation. Now, once we've done that, we note that the number of combined segments is equal to the original number of segments divided by 2. So it's equal to 1/2 the original number of segments. Okay, so what is the value for x1, which is the expansion of the last segment? Well, the length of x1, expanded length, is simply going to be d times the blended Hubble value times the time that light was traveling, all divided by CF. And that is exactly the same as we found in the segment finding dn. And the reason it's the same is because we're looking at the last segment and we're expanding it over the full length of time the light was traveling, which is the same transformation we had to make for finding dn. So since that is the expansion x1, the total of all the expansions is simply that amount times the number of combined segments, which is 1/2 d1 over d. And then simplifying this equation, the d's cancel. We can bring d1 out to the front to make it easier to look at, and it gives us this, that the total expansion for light over the time, for the time it was traveling, is equal to d1 times 1/2 hb times TL over the conversion factor. Now we recall this formula up here. dl equals d1 plus the change in the distance. And we're going to, for this, put in the amount we just calculated. And when we do that, we get this formula that dl equals d1 times 1 plus 1/2 hbtl over the conversion factor. And if we, just for convenience of writing things down, pick a variable, I just picked y for no particular reason, and let that equal all of this, 1/2 hbtl over CF, then this formula can be rewritten to give the value for d1 as d1 equals dl over 1 plus y, remembering that y is this expansion amount. And that's the formula we were looking for, which is, what's the amount for d1?